But, to get through, we'll compare what's new to what you already know from last year, and hopefully it kind of makes some sense. So let's start by recalling a situation, such as this one. Here's a one-variable function called f of x. If there's an x-coordinate on this function, we know that there's a tangent line here. This point will be called x naught, and then f of x naught, whatever that is. Okay, so that's kind of the picture we're looking at right now. And we say that f of x is differentiable, so this is kind of what you guys did last year, at this point, if, when you do the definition of the derivative, f prime of x naught, you do the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So we say that this function is differentiable at this point, provided that this limit exists. So that's what you learned last year, and we kind of saw that even with multivariable functions. So that's one thing that we need to keep in mind. We say that y equals f of x has a non-vertical tangent line at that point, because of this tangent line, and you can kind of see from the picture, we say that f of x can be closely approximated by a linear function near x naught. We also say that f is continuous at that point, x naught. So these are all kind of things that are natural assumptions from the stuff that you learned last year in calc. So if we want to look at a specific point on any given function, we know it's differentiable provided that we can compute the limit and take the derivative using the definition. That's one. We assume that there's a non-vertical tangent line if that's the case. That tangent line will approximate this function pretty close, in this general area. This tangent line is a pretty good approximation for what's going on with f of x. And we say that if it's differentiable and the limit exists, then it's continuous. Okay? Now, with multivariable functions, so this is in Calc 1. Let's say we have some function or some surface So here's f of xy. All right. Now we have a point corresponding to x naught and y naught that matches up to the surface. So maybe here. this point, what are the coordinates? X naught, y naught, and f of x naught, y naught. Okay? So the picture changes a little bit, but the analogs of what we talked about in Calc 1 is pretty much the same in Calc 3. So in Calc 3, we say that if f of x, y, actually let me reword that to keep it kind of the same. Sorry. F of x, y is differentiable at x naught, y naught if the limit exists. Let's just clean this up. So that's what we talked about yesterday. Just a little bit more long-winded instead of this. Okay? Because it depends which direction we're looking at, right? So I'm not going to write all those limits out. But assuming that the limit definition for the partial derivatives exists, then we say that it's differentiable. We say that z equals f of x, y has a non-vertical tangent, not line, but plane now, at that point, x naught, y naught, f of x naught, y naught. So now, maybe here, there's a tangent plane. The values of f can be approximated. Let's say values of f at x naught, y naught can be approximated by a linear function as well. And of course, f is continuous at x naught, y naught. Okay, so pretty much the same scenario we had in Calc 1, slightly different picture. Instead of a tangent line, there's a tangent plane now. However, we can still approximate what's going on at this point with a line. There is a linear function, a local linear function. Actually, there are several of them that will approximate what's happening here. We'll talk about those later. Probably not until tomorrow, though. Okay. Any questions on what we've talked about so far? Okay. Moving on. For f of x, y, the increment in f, or change in f, can be calculated by plugging in the change in x, the change in y, and then subtracting the starting point evaluated at f. Now, this can be approximated by something else, which looks very much like something you did in Calc 1. Do you guys remember how you approximated changes in y? Well, let's say if you knew the rate of change and you happen to know the change, wouldn't that tell you approximately the change in y? What's dy dx times, so the derivative evaluated at the point, that would be the rate of change, the slope, right? Times the change in x. So maybe off to the side here, in Calc 1, you approximated the change in y by taking the derivative at a point and then multiplying by the change in x. Does that look familiar?
No.
Not really? Okay. Well, what does this mean to you? What does it physically mean? It's the slope, rate of change, right? So if you know the rate of change and then you're multiplying it by the net change in x, that's essentially going to give you the change in y. So if you don't remember it, hopefully intuitively you kind of understand that that's approximately what this is. Can everybody buy that? Okay. So then the change in f, since we have a multivariable function now, is going to be, let me rewrite this down here so that we have more space, partial x evaluated at x naught, y naught, which represents the rate of change in the x direction. So if we're going in the x direction, naturally, we'll multiply by how much we changed in the x direction. But we're also going to tack on what? Partial y evaluated at x naught, y naught, and change in y. Okay? So this is how we can approximate.
When you're adding them?
Yes. Because there's two changes going on here. There's a little change. Essentially, okay. So if you imagine that this function here has a particular value and we deviate, a little bit forward, a little bit right. Does that make sense? So there's our delta x right here. Here's our delta y. This change is going to change the height of the function. It might be down or might be up a little bit. Does that make sense? But then this other change that I'm going to do, the change in y, is also going to change the height of the function. Does that make sense? So when you add them and combine them, that'll be like the net change in the overall height, which is z. Okay? All right. So we're building up to definition of differentiability, so just bear with me here. For delta x and delta y that are really close to 0, we want the error between, where'd that formula go? We want the error between the actual change, which is calculated this way, and the approximate change. We want that error to be smaller than the distance between the original point and the new point. So here's what that looks like algebraically. We want the error of delta f, which is the real change in f, minus the approximation, so minus partial x, evaluated at the point, times delta x minus partial y, evaluated at the point, times delta y. We want the error, which is calculated this way, to be smaller than the distance between x naught, y naught, which is our starting point, and our final point, which is x naught plus delta x and y naught plus delta y. Okay? So with all these conditions, here's finally your definition of differentiable. We say a function f of two variables is differentiable at x naught, y naught, provided that partial x exists and partial y exists, and the final piece, the limit as delta x and delta y both go to 0. Essentially, we're taking the limit of the error. So if we calculate the magnitude in error, we're comparing the error, which is delta f, minus the change in the approximate change, we're comparing that to the distance between the point x naught, y naught, and x naught plus delta x, y naught plus delta y. So what would the distance be there? The square root of what?
Delta x squared.
Good. Okay, so that's going to be 0. Okay. So, look, to be honest, here's what I need you to know so far, because this is kind of heavy stuff. You need to know this definition. You need to be able to apply this definition. However, not very often do you need to do this. Okay? Maybe one problem on an exam. The rest of them, we have some nice theorems that, so like for example, if I say, show that this is differentiable or continuous or whatever, you're not really going to use the definition too much because it's long-winded. There's a lot of stuff that needs to go on. The stuff that you're going to be dealing with most of the time is going to be a little bit more straightforward. Okay, so we'll do one example because you should know how to work with this definition and see how it actually pans out. But then we'll get to the stuff that you're going to be dealing with primarily. So let's say we want to prove that the function f of x, y equal to x squared plus, whoops, it should be 3y, is differentiable everywhere. Okay, so now if we're using the definition, the first thing we're going to do is calculate what this is. Okay? So delta f is the same as f of x plus delta x, y plus delta y, minus f of x, y. So now we're actually going to plug this into the equation and see what happens. So the equation is x squared plus 3y. So if I square the x term, that's going to be x squared plus 2x delta x plus delta x squared. I'm plugging in the x coordinate into f of x, y. Okay. Plus, I'm not done yet. I have 3y, right? So 3 times y plus 3 delta y if I plug it in. So this whole expression here represents just this first half. Okay? And now we're going to subtract f of xy, which is x squared minus 3y. So let's clean things up. What happens here? The x squareds go away. 3y's go away. All we're left with is 2x delta x delta x squared plus 3 delta y. Okay, so that's the real change in f. This second part of the numerator represents the approximate change, right? So now we're calculating what that's going to look like. In order to do that, we need to find partial x, which is what? 2x, partial y. Okay. And now I'm going to plug everything into the formula and find the limit. So now we do the limit as delta x and delta y go to 0 of 2x delta x plus delta x squared plus 3 delta y. And now we do, according to the formula, minus partial x, which is minus 2x, but we still need delta x. Do you guys see where I'm getting that from? What's the next term? Minus 3 delta y. All over the square root of delta x squared plus delta y squared. We're going to try to show that that limit is 0. If it's 0, then this limit exists, and since we're using just x's and y's, not a specific point, we've shown that this is differentiable everywhere. Okay? So let's see. These cancel. These cancel. Well, that's kind of nice. So all we're left with now is the limit of delta x, delta y going to 0 and 0 of delta x squared over the square root of delta x squared plus delta y squared. If only someone had shown you how to find limits that looked like this. Well, I guess I didn't show you exactly this problem, but replace the delta x with x squared, right? Nobody knows?
No.
Revisit what we did was it the first day or second day? Second day. When everybody was freaking out about limits, right? Oh, this section's so hard. When you're evaluating limits, there's 3 options, right? You can either plug in the values directly, which in this case, we can't because we get an indeterminate form. Or it's not going to exist, right? Which we would have to find different paths that have different limits. But why would we do that? We're trying to prove that it does exist, right? So that's not an option. What was the other option? We can't do L'Hopital yet.
Okay, change it to R.
There we go. Polar or substitution. You got to get this into one variable first. Does that ring a bell? Yeah. So if we change to polar, this is the same as the limit as r approaches 0 from the right. What's delta x squared turn into? Over, which is the same as the limit as r goes to 0 of just r cosine squared theta, which is the same as the limit as r approaches 0 of, well, actually, it's just 0. Yeah, I don't know why I wrote that. It's 0. Yay. Don't you just want 10 of those on your next exam?
No.
Wouldn't that be funny? You spend all this time learning all these things, and your exam is just 10 of these.
So that's like,
I'll see you guys tomorrow.